Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from Latent Space, featuring Myra Deng and Bissell from Goodfire AI. Their central claim is that the AI industry operates under a false premise. We assume models are linguistic entities we communicate with through prompts. They present evidence that prompting and direct neural editing are mathematically identical operations. Their research suggests controlling AI behavior requires abandoning conversation metaphors and adopting neurosurgical precision. This commentary unpacks their technical case and its implications. The standard explanation for AI hallucinations treats them as stochastic failures. When a model fabricates information, engineers typically reduce temperature settings to minimize randomness. Myra Deng and Bissell from Goodfire AI reject this diagnosis as technically incomplete. Their research identifies internal model states that correlate with fabrication events. They have isolated activation patterns representing uncertainty and user-pleasing behavior that precede hallucinations. Their data indicates models generate detectable signals before producing false information. The system is not randomly failing. It possesses internal markers of epistemic uncertainty that standard output layers do not surface. Their proposed solution bypasses prompt engineering entirely. Instead of adjusting external parameters like temperature, they advocate reading internal activation states to detect hallucination signals and suppressing them through direct weight modification. This technical approach connects to a broader theoretical claim about the nature of human AI interaction. The industry categorizes prompting as linguistic communication and weight editing as mathematical engineering. Goodfire references formal research demonstrating that in-context learning and activation steering converge mathematically under certain conditions. Their interpretation eliminates the conceptual distinction between language and code when interfacing with neural networks. They describe a calculable conversion ratio between prompt tokens and steering vectors. You can quantify how many adversarial text examples equal the magnitude of a single activation adjustment. This equivalence means typing instructions and modifying internal representations are not separate interaction modes, but identical operations expressed through different interfaces. Their critique extends to the industry's reliance on reinforcement learning from human feedback for alignment. The current training lifecycle applies reward signals to shape model behavior. Goodfire characterizes this methodology as structurally insufficient. They compare it to behavioral conditioning without explanation. Reward-based training modifies outputs without requiring the system to understand underlying principles. Their alternative framework, which they call intentional design, involves identifying specific neural circuits responsible for particular behaviors and editing them directly. Rather than conditioning a model through aggregate feedback, they locate the neurons encoding legal reasoning or political bias and modify those representations manually. Their empirical work reveals unexpected patterns in what models learn from training data. Standard assumptions predict that models trained on scientific datasets internalize scientific principles. Their findings contradict this expectation. During experiments with astrophysics models, they observe systems that accurately predict planetary motion without encoding Newton's laws. The model constructs alternative computational pathways that produce correct predictions within the training distribution, but operate through unrecognizable logic. This challenges the assumption that high performance implies human analogous reasoning. It suggests models develop alien cognitive structures that achieve correct outputs through fundamentally different mechanisms. They also present evidence for what they term subliminal learning, which violates standard data hygiene assumptions. The conventional approach assumes removing biased data from training sets eliminates corresponding biases in model behavior. Their research documents persistent hidden behaviors that survive distillation and data removal. Models exhibit latent tendencies, such as specific topic obsessions or political orientations, that remain detectable even after the original training data is discarded. Their explanation locates these behaviors in initialization noise or deep latent structures that standard distillation processes fail to eliminate. This produces a counterintuitive measurement result. Sophisticated interpretability tools like sparse autoencoders sometimes perform worse than simple linear probes at detecting these hidden behaviors. The more granular tool fragments concepts so thoroughly it loses the aggregate signal, while the simpler tool captures the raw activation pattern. Goodfire's technical work rests on a consistent principle. They reject treating neural networks as black boxes that respond to linguistic inputs. Their position is that meaningful control requires direct access to internal representations. Without the ability to read and modify neural states, they argue we are operating blind. The open question is, if we develop the technical capacity to surgically edit model cognition in real time, what governance framework determines which neural configurations are permissible? If you're interested in the video featured in this episode, click the link below to watch the original.